So this survey course of Introduction to Astronomy, there are many topics when I'm like, you could just take that and make a whole course on it. I know it. So I just want to kind of briefly touch on telescopes. Of course, we use telescopes to gather information from celestial objects, our cosmic messengers, and that the information we gather in electromagnetic radiation travels in little photons. And so we can call our telescopes affectionately photon buckets. So in order kind of importance, I don't know, we say that telescopes can do three things as they gather those photons. Probably the most important thing is that they can make the image that, compared to our naked eye, a lot brighter. They basically condense down the photons and they shoot it to us, so we get to see things more brightly. The other thing telescopes can do is we can make out detail, even, and we'll talk more about that in terms of angular resolution. Then the last thing, and sometimes we would tend to think this is the most important thing, but what telescopes can do is allow us to see farther away. So broadly speaking, there's two types of telescopes, two types of photon buckets. The first type is a reflecting telescope. And what reflectors or reflecting telescopes do is to use mirrors. So if you see a reflection, you think mirror. And so reflecting telescopes use this kind of parabolic or at least concave sort of shape, contact lens looking shape of a mirror to gather the light. The other type of telescope uses lenses, and it is called a refracting telescope. So if you're wearing glasses right now, kind of think of your two lenses. One of them actually is kind of what a refracting telescope would be like. And what happens is we have these lenses at the end of the tube for a refracting telescope. So whether it's a reflecting telescope, a reflector, or a refracting telescope, refractor, one of the things we try to do is, like I said, reveal detail. That would be the second I listed a minute ago. And the detail that we can make out of any object can be described by the angular resolution. So as it turns out, the sharper the image, the smaller the angular resolution. The sharper the image, the smaller the angular resolution. So you can imagine, I get asked a lot, so what telescope should I buy? Should I get one from Walmart, or is that good enough? And that's a hard question to answer. But it's what we say, the optics, it's how good the optics of the mirror, if it's a reflecting telescope, and the optics of the lens, if it's a refracting telescope, it's that quality that gets you things like angular resolution. I'm going to talk about size here in a minute, and sometimes we think that size is all, but it's not. You can see some really blurry images with a large telescope. And if it's blurry, that means your angular resolution stinks. So if you want to get better angular resolution, though, you need to keep this is assuming your optics, that the person who prepared your mirror or lens has done it correct with the correct shape. Getting over that assumption, then your best angular resolution, the larger the diameter of your mirror or your lens, then the better your angular resolution. Specifically, if you double the diameter, you double the details you can see. Angular resolution. So by definition, what that is the minimum angular separation that you can distinguish. So that's why the smaller down to a gnat's eyebrow that you can detail that you can see, that would be a better angular resolution. I like this. I'm going to show you this little animation. And basically, it's something that probably most of us have experienced. If you look down the road, nighttime, you see a car coming. And let's think of the car has two headlights, and let's kind of think how is the angular resolution changing of the image of the car as it comes towards me. So you see how what started out as a blob, I'll replay it, looking like one headlight, ends up being resolved into two headlights. Does that make sense? Okay, so that's kind of what we mean when we talk about angular resolution. So I think these are good too. Let me just show you kind of with the angular resolution. We said if you increase the size of your mirror if it's a if your mirror if it's a reflector, and of your lens if it's a refractor, then your angular resolution will decrease. So what this is I have a telescope over here, and it is actually looking at two stars over here, a red star and a blue star. And kind of like that far away, that the car lights when it was far away, this is all that I'm making out in the telescope. So the angular resolution is indicated down here, 1.250, and it's going to get smaller. The angular resolution is going to get smaller because what I have access to is to increase the diameter of this, this mirror for this reflecting telescope. All right, so I'm increasing it from 0.1, okay, to 0.5, 1.13. Okay, I'm increasing the size of my mirror and what's happening to the objects I'm seeing. I'm resolving them into actually two stars. And at some point we see them as basically pinpoints of light. Okay, so this is a, wow, this is a 10-meter mirror. Pretty darn big. All right, let me go ahead and make it smaller. I'm making my mirror smaller and smaller and smaller. My angular resolution is increasing. It's a poor, I can't resolve that I have two stars there. Okay, so that's size size makes a difference with angular resolution, but with size, you got to have quality. The other thing I want to show you, this is pretty intuitive, just if we picture increasing the size, and if our mirror down here really is a photon bucket, can you kind of see the increase in the photons that the bucket can collect? So we're starting out with a 0.1 meter mirror. I'm going to go ahead and increase it to 1 meter. And you can see as I increase it, increase the diameter. And by the way, the mirror reflecting telescopes, I get reflecting and refracting mixed up sometimes because they both start with the letter R. Reflecting telescopes have the mirror down here, and so the light rays come down, hit the mirror, and then they go, can you see where they bounce off? Because of the shape of the mirror, they both go back and they converge on a secondary mirror right here. Actually, they're not converging, they're going to ultimately then be bounced back one more time and converge down here. This is a type of reflecting telescope known as a Cassegrain, because, Cassegrain. It's known as a Cassegrain because the image is actually redirected out back through the primary or the main mirror. Let me go ahead and make the mirror as large as we can. Wow, look at all those photons being collected. That's a 5 meter in diameter, what we call primary mirror. Now the thing about reflecting telescopes that use mirrors is they are kind of more, how do I say, forgiving, and they're kind of easier to make in that we're going to silver the surface of the glass. And so underneath the glass we can have all sorts of support to kind of get exactly the right shape. So whether it's a reflecting telescope like this or a refracting telescope, you need to have the quality of your lenses there. So refracting telescopes versus reflecting telescopes, they're both photon buckets. And remember, refracting telescopes use lenses much similar to some of our eyeglasses. And so the reason they call them refracting telescopes when they use lenses is that it's called refraction when light is bent. And light is bent in a lens like this because light is going from air to the lens to air again. Those are three different mediums, if you want to count the air twice, right? And can you kind of see this bending here? That's called refraction. So light is bent in lenses. So more specifically, what we do in a refracting telescope is we use a lens. Like I think I mentioned, the lens is at the end of a tube. So here's my tube. Okay, here's where I'm going to view down over here. I guess right here. And light comes in straight, parallel lines of light, and then the light is bent, but it's bent specifically. This is a double convex lens. The light is bent so that it converges at what we call the focal point. Okay, so this is a refracting telescope using a lens to gather light to a point. Okay, so refracting telescope, here's the lens. Okay, this is what we call the tube. Here's the focal point right here. And then it has another eyepiece lens to what I say kind of unpack the image so that we can see it. So there's a focus here, and the eyepiece kind of brings the information back to another focus that we look. That's where we put our eye. So road trip, if you go see this telescope, which is actually near Chicago, it's the largest refracting telescope. I think, well, it says in the world. There you go. Up here is the lens, the 1 meter lens. Now, the thing about refracting telescopes is they aren't as forgiving and easy to make large as reflecting telescopes, because refracting telescopes, you can't support the back. If you can picture that, because we need light to kind of flow in down that tube and be brought to a focal point. So, and the other thing, you probably maybe have noticed this, but glass, and that's what lenses are made of. Glass is actually kind of, some would consider a slow-moving liquid. So over time, they kind of droop and sag, and then there goes your perfect shape. Isn't this beautiful, though? The Yerkes telescope. This telescope is housed inside of a dome. I don't know if you can kind of see this dome here. And domes have a slit, and here's the slit right here. If you come out to the Whitty Observatory Complex, you'll see that we have 2 domes, not nearly this big. And then what happens is this dome can kind of move around in a circle, and that makes that slit move. So you can put the telescope wherever you want to put it. So reflectors then use mirrors, and there are different types of reflectors, but what they have in common is they have it's supposed to be a parabolic shape. Where's my pointer? It's supposed to be a parabolic shape right here, but a lot of times it's more, I think more like spherical. Okay, but if it's parabolic, then what happens is the light comes in, parallel lines, and it hits this concave parabolic shape, and then that light is brought back to a focal point. And the way we get the information from the focal point then is what makes different types of reflecting telescopes. Okay, so this happens to be one type of reflecting telescope called a Cassegrain, and we looked at that a little bit ago on an animation. So you know it's a Cassegrain if you have a hole. Notice we have a hole in our primary mirror. Here's our primary mirror down here, and we need a hole because the light comes in. Okay, it hits the parabolic mirror, it goes back up here to a secondary mirror, and from the secondary mirror it comes to go ahead and converge to a focal point. Okay. Some telescopes, a real common design is is a Newtonian design, and what happens is we have a secondary mirror here that shoots it out the side, and you go ahead and observe it here. So again, they both use mirrors, but it's what you do with the image that you bring to a focal point. All right, so just some famous telescopes. Most research telescopes use mirrors. Most of them are reflecting telescopes. And oftentimes the mirrors are kind of segmented. Like, can you see the little, I guess it would be what, 6-sided blocks right here. And it works well if they're segmented for a couple of reasons. Assembling, and they can have a little bit more flexibility with the shape. So road trip. Okay, these are the Keck Observatory in Hawaii. Isn't that cool? And it's interesting because you would think Hawaii would there'd be too much kind of chronic cloud cover and that sort of thing, but I guess not. Now, we talked about different types of radiation, and we said that light is one energy of a family of radiations we call electromagnetic radiation. Radio waves is a type of electromagnetic radiation. So we actually then need to build radio telescopes that go ahead and gather photons in the radio wavelength energy end of the spectrum, gather those photons, and then what we do is make kind of what's called a false image of objects. So it's kind of interesting to see celestial objects, the radio information that they're sending us. So radio telescopes are a type of reflecting telescopes. Well, want to buy your own telescope? Here's a suggestion. You might want to start with binoculars. There are some really cool things you can see through binoculars. And I don't know if you've been getting those. There's something called skymaps.com, and that's where I get my sky maps from. And if you look at their monthly maps, and if you look at, for a given month, objects that can be seen, they will give a section for objects that can be seen through binoculars. Honestly, if you go the route of binoculars, another good thing is it will get you will have to become familiar with constellations, where things are at. And the technique of star hopping means that basically you see stars with your naked eye, but what you really want, the cool thing, and maybe see with your binoculars, is something between two stars that you found. So it's called star hopping. You find the star and then you kind of hop up, down, over, to get to the object you're looking for. So binoculars are a really cool idea. One thing is do not focus, no pun intended, on the magnification of the telescope you're buying. And remember that size is important, but quality is also important. And this is saying that if you get a telescope that the diameter of the mirror or the lens is too large, you know what's going to happen is it's going to be too much of a pain to get it out. So make sure it's portable. And I would encourage you just to get out there, maybe online or magazines, and to see what other people are buying or what they say about them. Being an amateur astronomer like myself is an ongoing hobby, and there's always things to learn. And I don't know, like I said, I just get out there. We do have a local astronomy club that I'm a member of, so remember that's through the Whitty Observatory Complex.